What if I told you that our most precise instruments, our atomic clocks, aren't just measuring time? What if they're actually sensing something deeper, a hidden structure woven into the very fabric of space-time itself? That's the wild idea we're going to dig into.
You know, we think of atomic clocks as the absolute gold standard for timekeeping. They're incredibly stable. But what if all that perfect ticking is actually picking up on something else? A faint whisper from a hidden layer of reality we never knew was there.
And that really is the heart of the mystery, isn't it? The idea that our clocks aren't just ticking, they're listening. They might be sensing a hidden geometry, a kind of internal structure to space-time. And if that's true, it points to a whole new layer of the universe.
To really get our heads around this, we have to start with a puzzle, an anomaly. Something strange that's been popping up in the world of high-precision physics, where your measurements are so good that even the tiniest little hiccup is a massive deal.
So this whole anomaly comes from something called a King plot. Now, according to all our best theories, the data on these plots should form a perfectly straight line. Simple as that. But here's the thing, they don't. Experiment after experiment shows these lines are bending, and that tiny little curve might just be pointing to a huge discovery.
Okay, so I've just thrown this term King plot at you. What on earth is it, and why is a little curve on a graph getting physicists so excited? Let's break it down.
In simple terms, scientists take different versions of an element, isotopes, and they measure these tiny little energy shifts inside them. Then, they plot the shifts from one kind of energy transition against the shifts from another. It basically creates a super precise map of how the atom's guts are changing.
And here is why that line is so important. If the plot is a straight, boring, linear line, it means physics is pretty simple. All those changes we see between isotopes can be explained by just two things we already know about, like changes in mass and the atom's electric field. But if that line bends, well, that means our understanding is incomplete. The atom is sensing a third, unknown factor that the standard model just can't account for. So what is it?
This brings us to a really fascinating, though definitely speculative, idea called the MMU framework. It says this something else isn't some new particle or force we need to find. No, it's the actual geometry of spacetime itself.
So in this MMU picture, spacetime isn't a smooth, continuous sheet. It's more like a crystal, a lattice. And the fundamental building blocks of this lattice are these little geometric units called cells, shaped like a kind of dual tetrahedron.
Now here's the crucial bit. Each of these tiny geometric cells can respond or kind of vibrate in three hidden ways. There's an electric mode, a torsional or magnetic mode, and a volumetric or gravitational mode. Think of them as the hidden degrees of freedom of space-time itself. And according to this theory, we never, ever see these hidden modes directly. Instead, everything we actually measure in our world, time, energy, you name it, is just a projection of these deeper internal vibrations. It's like we're just watching the shadows of a complex 3D object on a 2D wall.
Okay, so let's connect this whole projection idea back to our original puzzle, those bending King plots and our super precise atomic clocks. How do they link up?
In the standard view, right, when you measure time with two different types of atomic clocks, you should get the exact same answer. You're just measuring one universal, unchanging thing we call time. But the MMU view is completely different. It says that different clock transitions might actually be sensitive to different mixtures of those hidden electric, torsional, and gravitational modes.
This completely flips the script on what an atomic clock is. They stop being just passive timekeepers. They become active probes, geometric sensors of internal space-time response, capable of actually feeling the subtle vibrations of that space-time lattice. And just like that, the bending King plot isn't an anomaly anymore. It's evidence. The line bends for a very simple reason. The two atomic transitions being measured are sampling different combinations of those hidden space-time modes. The curve isn't a mistake. It's a natural projection effect. Now, a theory is only as good as its tests, right? You gotta be able to check it. And it just so happens, there's a perfect element to put these ideas on trial. Ytterbium. Ytterbium is really special because it gives us both sides of the experiment in one neat little package. The neutral ytterbium atoms, they are perfect for making those incredibly precise bending King plots. And then you have ytterbium ions, which are used in some of the world's best atomic clocks. It's the perfect, self-contained lab for testing if these two things are actually connected.
So let's pull all this together. What does this new way of thinking really give us? Well, it gives us a single, unified way of looking at these experimental puzzles that have been bugging people. See, this MMU idea suggests that king plots and atomic clocks are really two sides of the same coin. The bending plots are telling us that atoms can feel more than just two simple things. And if different clocks don't quite agree, it tells us that time isn't so universal after all. Both clues point to the same conclusion. Our reality is just a projection of a single, deeper, and way more complex geometry.
When you step back, it's a breathtaking thought that buried in the data from our most advanced labs, we might not just be tweaking what we already know. We might be catching the very first glimpse of the actual fundamental building blocks of our reality.
And that leaves us with this final, really provocative question. If this is even partially true, it means our instruments have been whispering these secrets about the deep structure of the universe for years. It just makes you wonder, what other profound truths are already sitting there in our data, just waiting for us to figure out how to listen?